Symmetrical fault current, often denoted as ISC, represents the maximum current that would flow through a symmetrical three-phase fault at the point of measurement. Ultimate symmetrical fault current, in this case 81,000 amps, signifies the maximum possible fault current that can occur under any fault condition. Understanding the distinction between these values is critical for electrical system design and safety. In general, the ultimate symmetrical fault current of 81,000 amps is used for two primary purposes. Firstly, sizing protective devices such as circuit breakers and fuses, and secondly, designing electrical systems to withstand the maximum possible fault currents. The symmetrical fault current of 24,000 amps, on the other hand, is typically used for two different applications. Firstly, calculating the interrupting capacity of switchgear and protective devices, and secondly, estimating the electromagnetic forces generated by fault currents. Regarding the division by 1.414, this operation is used to convert symmetrical fault current to line-to-line fault current. However, since the provided ultimate fault current is already a symmetrical value, no division is necessary in this specific scenario. As a rule of thumb, utilize the ultimate symmetrical fault current of 81,000 amps for electrical system design and protective device sizing. To elaborate further, let's delve into the specifics of each application. When sizing protective devices like circuit breakers and fuses, it is imperative to use the ultimate symmetrical fault current. These devices must be capable of interrupting the maximum possible fault current to prevent equipment damage, electrical fires, and potential injury. Selecting a circuit breaker or fuse with an inadequate interrupting capacity can lead to catastrophic failure during a fault event, potentially endangering personnel and property. For example, if a circuit breaker is rated to interrupt 50,000 amp symmetrical and the actual fault current exceeds this value, the circuit breaker may fail to clear the fault, resulting in a sustained arc flash and significant damage. Therefore, always refer to the ultimate symmetrical fault current when choosing protective devices. In terms of designing electrical systems to withstand the maximum possible fault currents, the ultimate symmetrical fault current is crucial for determining the appropriate conductor size, bracing of busbars, and selection of other components. Electrical systems must be designed to withstand the mechanical and thermal stresses associated with high fault currents. Failure to do so can result in conductor melting, insulation breakdown, and structural damage. For instance, if a busbar is not adequately braced to withstand the electromagnetic forces generated by a high fault current, it may become deformed or even rupture, leading to a complete system failure. Similarly, if conductors are not sized appropriately to carry the fault current, they may overheat and melt, causing a fire. When calculating the interrupting capacity of switchgear and protective devices, the symmetrical fault current is used. This value is important for ensuring that the switchgear and protective devices can safely interrupt the fault current without being damaged. The interrupting capacity of switchgear is typically expressed in symmetrical amps. For instance, a switchgear assembly with an interrupting capacity of 24,000 amps symmetrical is designed to safely interrupt fault currents up to that level. If the actual fault current exceeds this value, the switchgear may be damaged, leading to a loss of power and potential safety hazards. Estimating the electromagnetic forces generated by fault currents also relies on the symmetrical fault current. These forces can be substantial and can cause significant damage to equipment if not properly accounted for. The electromagnetic force is proportional to the square of the fault current. For example, a fault current of 24,000 amps can generate significant electromagnetic forces that can stress conductors, busbars, and other equipment. These forces must be considered when designing and installing electrical systems to ensure that they can withstand the stresses associated with fault events. The division by 1.414 is specifically used to convert symmetrical fault current to asymmetrical fault current. Asymmetrical fault current occurs due to the presence of a DC offset in the fault current waveform. This DC offset is caused by the inductance of the circuit and the timing of the fault initiation. The asymmetrical fault current is typically higher than the symmetrical fault current. The factor of 1.414 represents the square root of 2 and is used to account for the DC offset. However, since the provided ultimate fault current is already a symmetrical value, no division is necessary in this specific scenario. The ultimate fault current already represents the maximum possible symmetrical fault current. To further clarify the relationship between symmetrical and asymmetrical fault currents, consider the following. The symmetrical fault current is the RMS root mean square value of the AC component of the fault current. The asymmetrical fault current includes both the AC component and the DC offset. The DC offset decays over time, so the asymmetrical fault current decreases to the symmetrical fault current after a few cycles. Protective devices must be able to interrupt both the symmetrical and asymmetrical fault currents. The interrupting capacity of a circuit breaker is typically rated in terms of symmetrical amps, but the circuit breaker must also be able to handle the asymmetrical component. In summary, the ultimate symmetrical fault current of 81,000 amps should be used for electrical system design and protective device sizing. This value represents the maximum possible fault current that can occur under any fault condition. The symmetrical fault current of 24,000 amps is used for calculating the interrupting capacity of switchgear and protective devices and estimating the electromagnetic forces generated by fault currents. The division by 1.414 is used to convert symmetrical fault current to asymmetrical fault current, but this is not necessary when using the ultimate symmetrical fault current, as it is already a symmetrical value. Let's consider a practical example to illustrate the application of these concepts. Suppose you are designing a panel board for a commercial building. The utility company has provided you with the following fault current information. Firstly, the symmetrical fault current is 24,000 amps, and secondly, the ultimate symmetrical fault current is 81,000 amps. To select the appropriate circuit breakers for the panel board, you would use the ultimate symmetrical fault current of 81,000 amps. This ensures that the circuit breakers have sufficient interrupting capacity to safely clear any potential fault. You would also use the ultimate symmetrical fault current to determine the appropriate conductor size and bracing for the panel board. To calculate the interrupting capacity of the main switchgear, you would use the symmetrical fault current of 24,000 amps. This value is used to ensure that the switchgear can safely interrupt the fault current without being damaged. You would also use the symmetrical fault current to estimate the electromagnetic forces generated by fault currents, which is important for designing the switchgear enclosure and support structure. Another example could involve a motor control center, or MCC, in an industrial facility. The utility provides similar fault current values with a symmetrical fault current and an ultimate symmetrical fault current. When selecting starters and circuit breakers within the MCC, the ultimate symmetrical fault current is the critical value for ensuring adequate interrupting capacity. The bracing of the MCC busbars and the selection of conductor sizes would also be based on the ultimate symmetrical fault current to withstand the mechanical and thermal stresses of a fault. The symmetrical fault current would be used for evaluating the interrupting capability of the main incoming breaker to the MCC and for assessing potential electromagnetic forces. Always consult with a qualified electrician or engineer for specific guidance based on the unique circumstances of the electrical system. They can perform detailed calculations and analysis to ensure that the system is safe and compliant with all applicable codes and standards. Moreover, it is important to remember that fault current values can change over time as the electrical system is modified or expanded. Therefore, it is essential to periodically re-evaluate the fault current levels and adjust the protective device settings accordingly. Furthermore, proper coordination of protective devices is crucial for ensuring that faults are cleared quickly and effectively. Coordination involves selecting and setting the protective devices so that the device closest to the fault will trip first, minimizing the extent of the outage. This can be achieved through the use of time current curves, which show the tripping characteristics of different protected devices. In conclusion, understanding the difference between symmetrical fault current and ultimate symmetrical fault current is essential for designing safe and reliable electrical systems. The ultimate symmetrical fault current should be used for sizing protective devices and designing electrical systems to withstand the maximum possible fault currents. The symmetrical fault current should be used for calculating the interrupting capacity of switchgear and protective devices and estimating the electromagnetic forces generated by fault currents. Always consult with a qualified electrician or engineer for specific guidance based on the specific situation. Remember that safety is paramount, and proper electrical system design is critical for protecting people and property from the hazards of electrical faults. Proper selection of overcurrent protection is vital in electrical design and engineering. In the context of electrical engineering and safety, overcurrent protection refers to the measures taken to protect electrical circuits and equipment from excessive current, which can lead to overheating, damage, and even fires. Overcurrent can result from various sources, including short circuits, overloads, and ground faults. Therefore, it is crucial to implement effective overcurrent protection strategies to ensure the safe and reliable operation of electrical systems. There are several types of overcurrent protective devices commonly used in electrical systems, including circuit breakers, fuses, and ground fault circuit interrupters, GFCIs. Each type of device has its own characteristics and applications, and it is essential to select the appropriate device for a given situation. Circuit breakers are electromechanical devices that automatically interrupt a circuit when an overcurrent is detected. They can be reset after tripping, making them a reusable form of overcurrent protection. Circuit breakers are available in various sizes and interrupting capacities, and they can be used in both residential and commercial applications. Fuses are overcurrent protective devices that contain a fusible link that melts and interrupts the circuit when an overcurrent occurs. Fuses are typically less expensive than circuit breakers, but they must be replaced after they blow. Fuses are also available in various sizes and interrupting capacities. Ground fault circuit interrupters, GFCIs, are specialized overcurrent protective devices that are designed to protect people from electrical shock. GFCIs detect ground faults, which occur when current flows through an unintended path to ground. GFCIs quickly interrupt the circuit when a ground fault is detected, preventing electrical shock. GFCIs are commonly used in bathrooms, kitchens, and other areas where there is a risk of electrical shock. The selection of overcurrent protective devices depends on several factors, including firstly, the magnitude of the potential overcurrent, secondly, the voltage and current rating of the circuit, thirdly, the application and environment, and fourthly, the coordination requirements with other protective devices. It is important to carefully consider these factors when selecting overcurrent protective devices to ensure that they provide adequate protection. In addition to selecting the appropriate overcurrent protective devices, it is also important to properly coordinate them. Coordination involves selecting and setting the protective devices so that the device closest to the fault will trip first, minimizing the extent of the outage. This can be achieved through the use of time current curves, which show the tripping characteristics of different protective devices. Proper overcurrent protection is essential for ensuring the safe and reliable operation of electrical systems. By selecting the appropriate overcurrent protective devices and properly coordinating them, one can protect equipment, prevent electrical fires, and protect people from electrical shock. Always consult with a qualified electrician or engineer for specific guidance on overcurrent protection. And always remember to de-energize a circuit before working on it. Use proper personal protective equipment, or PPE, and follow all applicable safety procedures. Electrical work can be dangerous, and it is essential to take all necessary precautions to prevent accidents. Never work on electrical equipment unless you are qualified and authorized to do so. Electrical work should only be performed by trained professionals who have the knowledge and experience to do it safely. If you are not qualified, do not attempt to work on electrical equipment. Call a qualified electrician. Always inspect electrical equipment for damage before using it. Look for frayed wires, cracked insulation, and other signs of damage. If you find any damage, do not use the equipment. Have it repaired by a qualified electrician. Never overload electrical circuits. Overloading can cause the wires to overheat and create a fire hazard. Make sure that you are using the correct size circuit breaker or fuse for the circuit. If you are not sure, consult with a qualified electrician. Keep electrical equipment away from water. Water can conduct electricity and create a shock hazard. Never use electrical equipment near water unless it is specifically designed for that purpose. Use ground fault circuit interrupters, GFCIs, in bathrooms, kitchens, and other areas where there is a risk of electrical shock. GFCIs can protect you from electrical shock by quickly interrupting the circuit when a ground fault is detected. Be aware of the location of electrical panels and shut-off switches. In case of an emergency, it is important to be able to quickly shut off the power to the affected area. If you are unsure about any aspect of electrical safety, consult with a qualified electrician. Electrical safety is not something to be taken lightly. It is important to take all necessary precautions to prevent accidents. Ignoring the significance of safety standards and safety regulations may put yourself or the organization at risk. In any electrical system, safety must be paramount. The consequences of neglecting electrical safety can be severe, leading to personal injury, property damage, and even fatalities. Therefore, it is essential to adhere to all applicable safety codes and standards and to follow safe work practices. The National Electrical Code, or NEC, is a widely adopted standard for electrical safety in the United States. The NEC provides comprehensive guidelines for the design, installation, and maintenance of electrical systems. Compliance with the NEC is essential for ensuring electrical safety. Other important electrical safety standards include those developed by the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. These standards address a wide range of electrical safety issues, including grounding, bonding, overcurrent protection, and arc flash hazards. Arc flash is a dangerous phenomenon that can occur when electrical equipment is energized. An arc flash is a type of electrical explosion that can generate intense heat, pressure, and light. Arc flashes can cause severe burns, blindness, and even death. Arc flash hazards can be mitigated through the use of arc-resistant equipment, personal protective equipment, PPE, and safe work practices. Arc-resistant equipment is designed to contain the energy of an arc flash, minimizing the risk of injury. Personal protective equipment, PPE, such as arc-rated clothing and face shields, can protect workers from the heat and flames of an arc flash. Safe work practices, such as de-energizing equipment before working on it, can also reduce the risk of arc flash incident. In addition to arc flash hazards, there are other electrical safety hazards that workers need to be aware of. These include shock hazards, electrocution hazards, and fire hazards. Shock hazards can occur when workers come into contact with energized electrical equipment. Electrocution hazards can occur when workers come into contact with high-voltage electrical equipment. Fire hazards can occur when electrical equipment overheats or when flammable materials are ignited by electrical sparks. To protect themselves from electrical safety hazards, workers should follow safe work practices, use personal protective equipment, PPE, and be aware of their surroundings. Safe work practices include de-energizing equipment before working on it, using lockout-tagout procedures, and maintaining a safe working distance from energized equipment. Personal protective equipment, PPE, includes insulated gloves, safety glasses, and arc-rated clothing. Electrical safety is a shared responsibility. Employers are responsible for providing a safe working environment and for training workers on electrical safety hazards and safe work practices. Workers are responsible for following safe work practices and for using personal protective equipment, PPE. By working together, employers and workers can create a safe working environment and prevent electrical accidents.